Hi engineers! If you are aiming for a senior SDET or QA automation role at a top-tier tech company, listen up. The sliding window technique is a must-have in your toolkit. Why is this important? Because as an SDET, you are not just checking if the code works. You are responsible for performance testing and scalability. In the real world, processing millions of logs or data streams using nested loops will crash your system or make your automation pipeline painfully slow. Mastering this technique allows you to write high-performance scripts that run in linear time, making you a much stronger candidate for high-level engineering roles. Today, we are solving 3 different challenges using this exact same logic. Understanding the sliding window analogy. Before we touch the keyboard, let us visualize how this works. Imagine you are standing at a station, looking through a single train window. You can only see a specific number of passengers at one time. Let us say 3. This is your window size. As the train moves forward by one car, you do not need to recount everyone inside the car. You simply notice that one person left your view on the left, and one new person entered your view on the right. In coding, most people make the mistake of recalculating the entire window every time it moves. That is slow. With the sliding window technique, we only perform 2 operations. We subtract the element leaving on the left and add the element entering on the right. This keeps our performance lightning fast, regardless of how large the dataset is. The Big O notation deep dive. Let's talk numbers. So in an SDET interview, you cannot just say one way is faster. You need to explain Big O complexity. In a basic approach, we often see a loop inside a loop. Mathematically, if your array size is n and your window is k, that is O of n times k. If both are large, your performance drops off a cliff. With the sliding window, we only pass through the array once. Even though we are adding and subtracting, those are constant time operations. This gives us a time complexity of O of n. So to a lead engineer, hearing O of n is music to their ears because it means the code will handle 10 records or 10 million records with the same linear efficiency. Let's start with the foundation. Maximum Subarray Sum. We need to find the highest sum of any k consecutive numbers in an array. First, we define our function by creating a constant named Max Subarray Sum. We set this to an arrow function that takes an array called nums and a number k. Inside the function, let's create our first if statement. We check if the length of the nums array is less than k. If it is, the window cannot even fit, so we return null. Next, we create a variable using let named maxsum and set it to 0. We also create a variable called windowSum and set it to 0. Now we create a for loop to find the sum of our very first window. We initialize let I at 0 and run it until I is less than k. Inside, we take windowSum and add the value of nums at index I. Once that loop finishes, we set our max sum variable to be equal to the current windowSum. Now for the sliding part, we create another for loop. This time we initialize let I at k and we let it run until the end of the array. Inside this loop, we update our windowSum. We add the new element on the right, which is nums at index I, and we subtract the element that is falling off on the left, which is nums at index I minus k. To finish the logic, we update maxsum. We set maxsum equal to math.max, comparing the current maxsum with our new windowSum. Finally, we return maxsum. Now let's test our solution. We write a console log and call our function with an array containing the numbers 1, 2, 5, 2, and 8, and we pass in 2 as our window size. When we run this, the expected result should be 10. Next up is a circular array challenge. We need to replace every number with the sum of the next k numbers. We create a constant named decrypt that takes the array code and the number k inside. We create a constant called n and set it to the length of our array. Then, we create a constant called result and set it to a new array of length n filled with zeros. Now, let's create an if statement to handle the simplest case. We check if k is exactly equal to 0. If it is, we just return the result array of zeros immediately. Next, we define our window. We create a variable letStart and a variable letEnd. Let us create another if statement to set these. If k is greater than 0, we set start to 1 and end to k. Let's pause here. To make this work, we use the modulo operator. In a circular array, this is your best friend. Think of it like a clock. If it is 11 o'clock and you add 2 hours, it does not become 13. It wraps back to 1. When we write index modulo n, we are telling JavaScript to wrap the index back to 0 if it reaches the end. This prevents index out of bounds errors that crash your automation suites. Now, back to the code. We create a for loop that runs from start to end. Inside, we update window sum by adding the value of code at the index of I modulo m. Now, we create a for loop to fill our results array. We initialize let I at 0 and run it for the length of the array. Inside this loop, the first thing we do is set result at index I to be equal to our current window sum. Next, we perform the actual slide logic line by line. First, we subtract the element that is currently at the start of our window. We write window sum minus equals code at the index of start modulo n. After we subtract that value, we need to move our start pointer forward, so we write start plus plus. Next, we need to move our end pointer forward to capture the next number in the sequence, so we write end plus plus. Finally, we add the new element that has entered our window on the right side. We write window sum plus equals code at the index of end modulo n. Again, we use that modulo operator to ensure that if our end pointer goes past the last index, it wraps perfectly back to the start of the array. Once the loop has finished processing every index, we simply return our result array. Now, let us test our solution. We write a console log of our function and pass in an array with 5, 7, 1, and 4, and a key of 3. When we run it, the expected result should be 12, 10, 16, 13. Finally, let's solve a string-based problem, minimum recolors. We want to find the minimum number of white blocks to change to black to get k black blocks in a row. We create a constant named minimum recolors, and take in blocks and k, we create a variable let whites and set it to 0. Now, we create a for loop to check the first window. We initialize let I at 0 and run to k. Inside, we create an if statement. If blocks at index I are equal to the letter W, we increment whites by 1. Next, we create a variable let min operations and set it to the current value of whites. Now we slide. We create a for loop starting with let I at k. Inside, we create an if statement to handle the left side. If the block leaving the window, which is blocks at index I minus k, is equal to W, we decrement whites. Then we create another if statement for the right side. If the block entering the window, which is blocks at index I, is equal to W, we increment whites. We update min operations to be the math.min of itself, and the new whites count. After the loop, we return min operations. Now, let's test our solution. We write a console log and pass in the string WBBWB and W. And we set our target k to 7. Since there are 4 W characters in that 7-character string, the expected result should be 4. Interview tips and real-world use case. You might be thinking, when will I ever sum numbers in a window while testing? Think about log analysis. If you are monitoring a server response time and you want to find the highest average latency over any 5-minute window to detect a memory leak, this is exactly the algorithm you would use. When an interviewer sees you using a sliding window, mention these things. Explain the linear time complexity. Talk about the constant space complexity. Mentioning edge cases, like what happens if the array is empty, shows you are thinking like a professional SDET. If you found this breakdown helpful, hit that subscribe button. Drop a comment below with your most recent interview coding algorithm, and we will solve it together in the next video. Now you're 1% smarter. The cheat code is consistency, so keep boosting your brain. Make it your daily routine, and you will nail your next interview. Same rhythm tomorrow. At CodeCrack Interviews.